Yeah, so today we are going to talk about industrial applications of electrolysis and also this whole idea of something being discharged and something being ionized, that whole thing. So we're going to talk about that today. The industrial application, like how useful is this whole thing? So it turns out it's pretty useful, pretty useful when it comes to many applications. So two of them that are I'm going to mainly focus on. The first one is electroplating. Electroplating simply means that you have something. So, for example, you have a ring or a watch, and you want that it shouldn't rust, or you don't want it to be damaged by friction or by rubbing with other things or something. So, you want to have a coating of something that is more durable on it. Or maybe you have some piece of something that you need to make more shiny or more beautiful. You just want it to be look better. So electroplating can also help us there. So what you do is you plate a layer of one metal on that. So usually we do it with precious metals like gold, silver, platinum. We plate stuff with that. It looks better, it increases in value, and it sells for a number of reasons. We also need to plate stuff when we want to, for example, if you have wires and you want them to conduct better, then you would like to have wires made of really good metals like gold. So if you're making wires for a space shuttle and you have a big budget, you might want to make wires from gold. But then you also want to make sure that those gold wires are plated with some other metal, maybe to offer a cushion or something. So electroplating can help us over there as well. So we do electroplating for multiple reasons. We do it for things to become more beautiful. We do it for things to become more valuable. We do it to save money. For example, if somebody wants to get jewelry and getting a jewelry made from high quality gold or more pure gold, like 24 carats is too pure, maybe just 22 carat gold or 20 carat gold, that might be a little more expensive than just getting something made from silver and getting it plated, or something made from copper and getting it plated. And that is what many people do. They get something made of a less valuable metal and they plate more valuable metal on top of that. Similarly, for example, if you are looking to buy a watch, then you just want to have you have your unique taste of watch, and you're like, okay, I want a watch that is plated with platinum or that is plated with gold. So a watch made from pure gold will be quite difficult to make for the watch manufacturer. But what they can do is they can make the watch with whatever stuff they usually make and then plate it with your choice of metal. So people do it with iPhones, people do it with jewelry, with watches, with so many things. Okay, so electroplating is allowing us to do that. So what exactly is it? You plate a metal on another metal. How are you able to do that depends on the fact that whatever you want it to be plated on, you want that to be the cathode. So for example, this ring, I want it to be plated with gold. So I would like that gold ions come and attach themselves or deposit themselves over this ring. So what do I want? I want this ring to be connected to the negative terminal so that it gets a negative charge. So it gets a negative charge and starts to attract positive ions. And what positive ions do I want? I want ions of gold. So maybe I take a piece of gold, something that I want to plate on this. And now that piece of gold has positive charge. The ring has a negative charge. And now I just want to find a way for these ions from gold side to come and travel to this ring, which is the negative side. So what do I do? What do I need? I need an electrolyte. So usually we take the electrolyte of something that has the same ions as this metal, but it's not necessary. As long as this metal is more reactive than the electrolyte, you can do the as long as this metal is less reactive than the electrolyte, you can do the electroplating. Why? Recall the rules that we talked about. We said that a reactive ion discharges, ionizes. So a reactive anode will ionize, it will form ions of its own. So we take a metal that we want to plate. So for example, if I want gold, gold is a reactive anode. It's very less reactive, but still reactive to some extent. So I take gold, or maybe I take copper. I want to plate something with copper. Then I will take copper as that metal that I want to plate. And I need an electrolyte. So that electrolyte might be some salt that has this thing. So for example, usually we take copper sulfate as the salt because it has copper, and copper is less reactive than hydrogen. So even though you have water in there, it will not plate itself. So let's suppose I want to plate this thing with gold. So I take gold as the rod that I have, and I give it a positive charge. So here's the thing. I have electrodes, and they are not inert. One of them is the ring that I want to plate on, and one of them is the gold piece that I have. Sorry, this should be AU. So I want to plate that gold piece over there. The electrolyte that I have is copper sulfate, which is aqueous, and it is dilute. Okay, so what ions do I get? What happens at the anode and what happens at the cathode? So these are the three answers that I'm looking for. So first of all, let's look at the electrolyte that you have. You have copper sulfate and water. So copper sulfate will form copper ions and sulfate ions. And water will make hydrogen ion and hydroxide ion. But you also have gold in there. And remember the first rule. First rule said a reactive anode ionizes. So do you have the anode here? Yeah, you do. This thing is positively charged. So this is anode. So what's going to happen is that this gold is going to form gold ions. So now you have gold ions, which simply means that you have gold dissolved into the electrolyte. So you will see gold ions falling down into the electrolyte. Okay. So at the anode, you take pure gold and it converts to gold ions and loses electrons in the process. What happens at the cathode? So remember the second rule. This rule was less reactive ion discharges except concentrated halogen ion. Less reactive ion discharges except concentrated halide ion. What is the less reactive ion? So these are the three positive ions that you have: hydrogen, copper, and gold ions. Which is the least reactive one? Gold. So gold goes over there. It is positive 2. It takes 2 electrons and makes gold. So if you look at it, ये क्या reaction? At the anode, you take gold, it forms ions. At the cathode, those ions convert back to gold. तो हमें क्या फायदा हुआ? हमें फायदा ये हुआ that gold ions have actually gone from the anode, from here to here, and you will see a layer on top of this thing, and it will be a very uniform layer. How many electrons has it used? For every one atom of gold, you need 2 electrons. So to get 1 atom of gold over here, you need 2 electrons. So if I say that, all right, I have 1 million atoms of gold, that means 2 million electrons have been used. So what will happen once you run out of gold? If you run out of gold, then all the gold is gone. You have copper and hydrogen left. So copper will start to plate on top of that, which is why it's very important that when you're doing this, you time yourself. You make sure that, all right, by this time, all the gold that I've needed to plate has been plated. So you stop the reaction. You don't want copper to be plated on top of the gold. You don't want that. Okay. Also because that defeats the whole point. And secondly, because gold is expensive, you don't want to damage it. All right. So this is electroplating. So what happened here? First of all, whatever you wanted to plate on, so if it is a jewelry, it's a watch or whatever it is, you put that thing as the cathode so that it can attract cation. And whatever you want to plate it with, so gold, silver, whatever you do, you place that thing as the anode. Why? Because the first rule says that reactive anode ionizes or forms ions. So this anode will form ions. And that's the only reaction that happens at the anode. Notice that you did not get oxygen, you did not get anything on the anode because anode itself dissolved. And that is electroplating. Now, interestingly, let's suppose somebody took the same thing, and instead of having gold, they took copper. So they have copper metal. That's going to be pink in color, okay? Now what will happen? At the anode and the cathode, let's see. So they have a ring over there and they want to plate it with copper. So you have two positives. First of all, the anode is copper, so it is reactive. So if you have the reactive anode, that's the first rule. If you have reactive anode, it ionizes. So copper will form copper ions by losing 2 electrons. So copper converts to copper ions. Remember this thing. Copper metal is pink, but copper ions are blue. Okay, in water. So copper metal will be pink. So you will see pink rod over there, which starts to dissolve and the color of the solution starts to become blue. Now, if you already had copper sulfate in there, if you already had that, then you will notice that the color starts to darken. Why? Because copper sulfate itself has copper ions in it. So you already have copper and you're adding more copper to it. Okay, what happens on the other side? So the copper goes over there, the copper ion goes over there, gets 2 electrons, and it forms copper metal, which is pink in color. So on this side, you will see pink solid coming up and depositing. What happens to the color of the solution? So you had copper metal, which dissolved, so it formed copper ion, and then that copper ion went and placed to become copper metal again. So overall, the color does not change. Interesting, no? Now let's suppose I do the same reaction with one small change. So I have the same, so I have this ring. So this is electrolyte, this is the ring, and this ring has a negative charge, and there's a copper piece of copper. So this is copper. And this time I have sodium chloride aqueous, and this is dilute. Okay, nothing else has changed. I just changed the salt that I was using. So what electrodes do I have? I have copper electrodes. What electrolyte do I have? I have sodium chloride aqueous. What ions do I have? I have H positive from water, OH negative from water, sodium positive, chloride negative, and because of the copper ion being reactive, I have copper ion. What happens at the anode? You know that anode here is reactive. So copper changes to copper ions. Why? Because a reactive anode, if you have that, it will form ions, and that's exactly what's happening here. It's forming these ions. What happens at the cathode? You'll get that same copper ion. Why copper ion? Because you have just 3 positive ions, these 3, and copper is the least reactive one. So the least reactive discharges. So copper ion goes, gets 2 electrons, makes copper. Now here's the thing. You will notice that on the right side, this starts to dissolve. And while this is pink in color, the solution turns blue. But after a while, these blue ions come over here and they start to plate on that, which means you will see a pink layer and the blue color fades. So interestingly, you will see blue color coming from right to the left side because copper ions are traveling. And once all the copper ions have been deposited, the solution will turn colorless. Okay, so the solution changes color if you're adding a copper ion, and it did not have that before, but on the left side, it already had copper ions from copper sulfate. So it's not changing any color. All right, and that is electroplating. So a few important points to remember. Number one, the thing that you wanted to plate on, you make that cathode. Why? Because you want the cations to come over here. Number two, the metal that you want to plate, you put it as the anode. All right, then let's move on to cells. What is a cell? A cell is anything that produces electricity. So far, we have been looking at batteries that provide electricity. We haven't really talked about a cell. A cell is just the most basic unit that produces electricity. So how does it do that? To produce electricity, you need electrons that have some energy that makes them travel from one place to another, right? That's what we need. So how does it work? So what happens is you have an electrolyte, a liquid that conducts electricity, and you have these rods. So it looks a lot like the electrolytic cell that we had. But there's one small difference. In the electrolytic cell, we would have placed a battery here. But this time we are not going to do that because we don't want battery. We need to produce our own electricity. So what we do is we put voltmeter here, and that voltmeter will simply tell us the voltage between 2 points. Why is that important? Because voltage is simply how much energy any charge has. So this voltmeter tells me how much energy or how much extra energy is on the one side compared to the other side for every charge. So that's why I take the voltmeter and I place it like that. And obviously, if they're both, let's suppose this is copper and this is also copper, then that's it. Nothing happens. Why not? Because the charges or the electrons in copper, so the charges in both the sides are at the same level. But let's suppose I replace one of these. Instead of having copper here, I put iron. Now what happens? We know that iron is more reactive and copper is less reactive, which means that electrons in iron kind of have a higher energy than those in copper because they're more reactive. So what happens? The electrons from iron start to travel to copper. So iron becomes iron ion because it loses electrons. And copper gets a negative charge because all these extra electrons that iron is losing are coming and accumulating over there. So iron makes iron ions and copper gets a negative charge. And then eventually what happens is that these iron ions are over here in the electrolyte. They may travel over here and get these electrons back. But in this process, we have conducted electricity. Now let me replace iron with something like calcium. Now, same thing will happen. Calcium is more reactive than copper. So calcium will change to calcium ions. So these electrons will travel and calcium ions will then be dissolved and they can eventually travel to copper and get that. Once all the copper calcium has been used up, we say that the cell has run out because no more calcium ions can be made, so no more electricity will be conducted. Now, if somehow you were to convert those calcium ions back, you will say that you have recharged the cell. If calcium ions were to convert back and make calcium, so the whole process could be started again, you could say that we have recharged the cell, and that's it. Now, how is irons more different than calciums? So the voltage, let's say this is voltage 1 and this is voltage 2, you will see that the second voltage is much higher than first voltage. Why? Because calcium is more reactive than iron. But that just tells us half of it. Actually, if you look at the reactivity series, so one of your metals is over here and one is over here. So iron is converting its electrons and sending them to copper. But compared to calcium, the difference in electricity or the difference in reactivity is much, much higher for calcium and copper than iron and copper, which is why the voltage between calcium and copper will be very high. So the voltage between calcium and copper will be higher and between iron and copper will be lower. And that is how a cell works. If you have copper on both sides, then there is no difference in voltage. So there is zero voltage. But the more reactive, the further apart these things are, the faster the electrons travel or the higher voltage they produce. So if you were to take, let's suppose, aluminium and zinc, and you were to take magnesium and iron will produce a lot more voltage than aluminum and zinc. Why? Because magnesium and iron have a much larger difference than that of aluminum and zinc. So that is how you make electricity. The most basic cell. Now there is a very useful cell that people are using more and more these days. That cell is called a fuel cell. There are many different kinds of fuel cells, but we are going to talk about the one that uses hydrogen and oxygen. So this is the cell that we use to power space shuttles or rockets. This is also is currently being used to produce electric vehicles. And I think San Francisco has more than 10,000 of the vehicles that use fuel cell. What makes fuel cell very special is that it is very clean. It only produces water, which means that it is very good for the environment. There is no harmful gas being produced. So how does it work? The detail of fuel cell is not in your syllabus. We study that in A levels. But here's what the general idea is about. So you have a fuel cell. It has two metal rods. So these are two metal rods. There is some electrolyte in there. From one side, you're going to get oxygen. From the other side, you're going to get hydrogen. So what's going to happen? This hydrogen will come in and be absorbed over here, and this oxygen will come in and be absorbed over here, and they will form ions. So hydrogen forms these hydrogen ions, and oxygen comes in, and through some process, we don't need to know about that process in detail, it reacts with water and produces, so oxygen and water and these electrons that hydrogen has provided, they react and they make hydroxide ions. So the water in there, which is the electrolyte, and hydrogen's electrons, they are all used up with oxygen to make a hydroxide ions. And then this hydroxide ion can react with hydrogen ion and make water, and water is sent back. Which means that this thing used water and produced water, except hydrogen and oxygen were also used up. So what's good about this is that no harmful gas is produced. You can take energy from here. So I can literally connect a bulb over here between these two metal rods, and I will see bulb light up. People are running cars on it. We have been using it for rockets and space shuttles for a really long time now. So this is a good process. You don't need to know about these equations in detail. They will give you these equations if there is a question. What you do need to know is the usefulness of fuel cell. Why is it a good thing and why is it a bad thing? So it's a good thing because it does not produce any harmful gases. It's a good thing because it makes water. It's a good thing because it is very portable and it produces a lot of electricity for a very short amount of fuel. The fuel here is hydrogen and oxygen. Oxygen you can get from the air, but hydrogen you'll have to get from some tank. And that is where the problem comes in. Hydrogen is explosive, which means let's suppose there's a car that has hydrogen tank in it. And unfortunately, that car has an accident. So now, if the tank breaks up, then this hydrogen can explode. There's a chance that it will. Which is why for daily life, fuel cell poses that problem. That if there is a leakage of hydrogen gas for an accident or some other reason, then it can be life-threatening. If you can resolve that, then you might have just solved world's energy problem. And that's it for electrochemistry. All right, then take care.